We have mapped billions of distant galaxies, yet our ability to detect immediate local threats remains dangerously fragile. On May 10, 2026, the Mount Lemmon survey identified near-Earth object 2026 JH2. Just days later, on May 18th, its trajectory crossed Earth's path at a distance of approximately 90,000 kilometers, roughly a quarter of the way to the Moon. Astronomers measure this risk using the Earth Minimum Orbit Intersection Distance, or MOID. For 2026 JH2, the MOID was an extremely close 90,180 kilometers. Based on its brightness, the object is estimated to be between 16 and 35 meters in diameter. The total time between its initial discovery and its closest approach to Earth was just 8 days and 16 hours. In that brief window, astronomers managed to track the object only 24 times, leaving a high degree of uncertainty in its exact orbital path. This 8-day window represents a systemic limitation in current ground-based observation networks. Understanding why our most advanced telescopes miss these specific local threats requires looking at the physical limits of optical detection itself. Objects in the 15 to 35 meter range are often dismissed as small in cosmic terms, yet they command immense priority in planetary defense architectures. To see why, we look at the historical baseline for this specific size class, the February 2013 Chelyabinsk meteor. The massive secondary damage and thousands of casualties in that event were caused entirely by an atmospheric shockwave rather than a physical ground impact. The Chelyabinsk impactor was 18 meters in diameter, with a mass of 9,100 tons. It entered the atmosphere at 19.2 kilometers per second, at a shallow 18-degree angle. That specific combination yielded an energy output of 400 to 500 kilotons, detonating at an altitude of 30 kilometers. Because objects like 2026 JH2 carry this exact kinetic potential, an 8-day warning window is mathematically insufficient to mount any meaningful civil defense or orbital deflection. The Vera C. Rubin Observatory and its upcoming Legacy Survey of Space and Time, or LSST, represent humanity's most powerful optical sky survey to date. Recent simulations using the SORCHA survey software evaluated the LSST's theoretical ability to find imminent impactors before they hit Earth. For large objects over 140 meters, LSST projects a 79.7% discovery rate and a 1,200-day warning time. But for small 10 to 20 meter objects, discovery plunges to 10.5%, and the warning time shrinks to just 12.4 days. The primary physical constraint driving this severe drop-off is known as photometric sensitivity. Astronomers estimate an asteroid's size using a combination of its absolute magnitude, or brightness, and its estimated albedo, which is its surface reflectivity. A Great-Stilney asteroid might have an albedo of 0.25, reflecting 25% of incoming photons toward a telescope. A dark carbonaceous asteroid, however, absorbs up to 95% of that light. Because optical telescopes rely on reflected light, these dark, small asteroids act like cosmic stealth objects, invisible until they are in our immediate vicinity. Beyond raw sensitivity, there is a secondary architectural limitation: observing cadence and data linking. Telescopes like the LSST do not stare continuously at one patch of sky. They scan in sweeps, capturing discrete snapshots over time. The Solar System Processing Software pipeline requires multiple discrete observations across several consecutive nights to confirm an object's orbit. This confirmed string of linked observations is called a tracklet. Fast-moving near-Earth objects traverse the telescope's field of view too quickly. They exit the frame before the system can establish the second or third point needed to link the tracklet. Finally, there is one last compounding point of failure: the solar exclusion zone. Optical telescopes are blinded by the sun's daylight glare. Any asteroid approaching Earth from the day side is completely hidden in that radiation. When you combine dark surfaces, fast orbital movement, and solar glare, ground-based optical surveys hit a hard physical limit for detecting imminent small impactors. Closing the 12.4-day warning gap requires a transition from optical reflection to a different part of the electromagnetic spectrum. The engineered solution is NASA's Near-Earth Object Surveyor Space Telescope, currently scheduled for launch in 2027. This mission shifts from optical to infrared observation, designed to detect the thermal heat emission of an asteroid rather than its reflected light. Infrared detection neutralizes the albedo problem. A dark asteroid absorbs more sunlight, which actually makes it glow brighter in the infrared spectrum. The NEO surveyor will be parked at the Sun-Earth L1 Lagrange point. Positioning the telescope 1.5 million kilometers towards the Sun allows it to look continuously outward, entirely eliminating the solar exclusion zone. Moving to a space-based infrared architecture bypasses the atmosphere, counters dark surface absorption, and removes the visual constraints that cripple ground surveys. But early detection by the NEO surveyor is only the first phase. Physically characterizing the threat is the crucial second step. In April 2029, the notorious asteroid Apophis will make a historically close flyby of Earth. To capitalize on this, the European Space Agency and the Japan Aerospace Exploration Agency formalized the Ramses mission, designed to rendezvous with Apophis and observe it precisely during this close approach. Ramses will measure exactly how Earth's tidal gravity physically pulls and deforms the asteroid's internal structure as it passes. Observing this tidal deformation provides an in situ kinetic model. Engineers need this exact data to design future deflection payloads, like gravity tractors or kinetic impactors. This creates a unified planetary defense architecture: optical deep sky mapping by the LSST, infrared early warning by NEO surveyor, and kinetic modeling by Ramses. This multi-layered international approach provides the architecture required for a predictive, actionable planetary defense.